I found this picture online to explain this question. You can see here that when k equals to 1, the decision boundaries are very rough. That's because, say, you have a test data here. K equals 1 means you only depend on one neighbor that's nearest. This portion would be red. Whereas if you look at this green part, any point in the green part will have a nearest neighbor here as green, so it will be classified as green. But then as you increase the k value, it relies on more points to make a decision, which makes the decision boundaries smoother as you increase. This is somewhat nicer because if you have a new test set, which is not in the training set, you don't want to rely on a few of the neighborhoods to make a decision. Having good accuracy on the training set, but doing poorly on the test set is what we call overfitting. We say a machine learning algorithm overfit the training set if that happens. And you can see here, it will have a very good performance on the training set, but you can imagine that once you apply this into some test set, it's not going to be doing well. So the answer is D. A given data set has 5 items in group 0 and 4 items in group 1. A decision tree at the root node used the feature to split the data into 2 sets where the first set had 3 items in group 0 and no items in group 1. All other items went to the second set. Find the information gained at the root node. So here what we want to do is we want to calculate the entropy before and after this split. So let's think about the before split. So before split, what's happening is that there is 5 in group 0, 4 in group 1, which means there's a 5 out of 9 probability for, or let's just say probability of being in group 0 is 5 over 9, and probability of being in group 1 is equal to 4 out of 9. Now, the entropy is calculated as the expectation value of the log. And although it's standard to take log of 2, for machine learning purposes, it doesn't really matter if you use log 2 or log base e, which is ln. So we're just going to use ln, and that's what this sentence means. Just use ln. That's because ln of 2 is not so easy to do it for a calculator. So let me pull up. Okay, so let's try to calculate the entropy. So entropy is defined as negative of sum of pi times ln of pi. So it will be negative of 5/9 times ln of 5/9 plus 4/9 times ln of 4/9. Okay, so let's put that into the calculator and see what we get. Okay, so let's put a parenthesis around 5 over 9 and times ln of 5/9 and then plus 4 divided by 9 and then times, well, let's do 4 times 9. That way we don't have to worry about whether this log will get multiplied in the numerator or the denominator. So 4 divided by 9, and then we will divide it by 9. Okay, so that's what you get, and I didn't put a minus, so it's really, the actual value is 0.68696. Okay, So that's the entropy. And now let's think about the entropy after split. So after split, there are two groups, right? So in the first set, you have 3 in group 0 and none in group 1. Okay, so that means you have probability of 1 for being in 0, right? It's just 1. There is no other case, which means that when you take pi, ln, pi, you get ln of 1, but ln of 1 is 0, so your entropy will be 0. So if you ever have a case where you only have one group, then entropy will just be 0. That's something nice to know, okay? Now the second set has, well, see, before we had 5 in group 0 and 4 in group 1, but then 3 of the group 0 guys went to the first set. So in the second set, you'll have 2 in group 0 and 4 in group 1, which would mean that it's very similar to this. P of x equal to 0 would be, but now it would be 2 out of 6. And P of x equals to 1 is equal to, it's 4 out of 6, which is like, this will be 1/3 and this is 2/3. Now let's do the same calculation. So we do 1 times ln of 1/3, and then I divide it by 3. Oops. Divide by 3, and then plus 2 times ln of 2/3, and then divide by 3. Okay, and you get negative 0.63651. So entropy is equal to 0.63651. Okay. All right. But then you have to think about the entropy as a whole. So what you need to do is you have to take the weighted average of the two. So there are 3 groups in the first set and 3 elements in first set and 6 elements in second set. So what we need to do is we have to take the weighted average of 0 and 0.63651. So let's do that. So we're going to take 3 items belong to the first set, which has 0 entropy, plus 6 items belong to the second set, which has 0.63651 as the entropy. And then you divide this by 3 plus 6, which is 9. So you end up with 0.42434. Okay, so you can say that the weighted average of entropies is equal to 3 times 0 plus 6 times 0.63651, and then divide by 9, and that's equal to 0.42434. 0.42434. Okay. Now, what is the information gain? Well, the more information you have, you reduce the entropy. So, entropy. So, anytime you go down to the decision trees, you're gaining more information. And the difference between the entropy before and after each node is called the information gain. So what we need to do is we have to take this number minus this number. Okay, so let's do that. So let's put 0.68696 and then minus 0.42434, and if you to enter, it's 26262, and the answer is A. Using a data set of Maritime College students, we want to build a decision tree for predicting who gets accepted for cadetshiping. One feature set is the number of demerits. Among the applicants, 80 students had 0 demerits, 40 students had 1 demerit, 20 students had 2 demerits, 50% of those with 0 demerits were accepted, 30% of those with 1 demerit were accepted, and only 10% of those with 2 demerits were accepted. What is the Gini impurity index for the feature demerits? So when you try to build a decision tree using the CART algorithm, you use the Gini index, and you calculate the Gini index for various features, and you start by using the Gini index with the lowest number, and that's how you build a decision tree. So let me explain how to get the Gini index here. The Gini index is defined as either sum of pi times 1 minus pi, and it's also equivalent to, you get the same value if you did 1 minus sum of pi squared. And what we need to do is we have to calculate this Gini impurity index for each of these groups, and we have to take weighted average because the sizes of these groups are different to get the final Gini index. So let's start with probability of 0 demerits with probability accepted. Okay, so and well, it's like, what is the probability of it being accepted under 0 demerits? Well, that probability is 50%, 0.5, and therefore the probability of not being accepted is also 0.5, okay? Also 0.5. So if I go by this formula, the second formula here, the Gini index, I'll just call this G1, that's going to be 1 minus 0.5 squared plus 0.5 squared, and that's going to be 1 minus 0.25 and minus another 0.25, which is going to be 0.5. Okay, good. 1 down, 2 more to go. The second one is the people with 1 demerits. So in that case, we have 1 demerits is 30% accepted and 70% not accepted. So it's going to be G2 is going to be equal to 1 minus 0.3 squared plus 0.7 squared, and that's going to be equal to 1 minus 0.09 minus 0.49, which is going to be 0.42. Okay, and again, with 2 demerits, it's only 10% acceptance, so it's going to be 0.9 here, and then G3 would be equal to 1 minus 0.1 squared would be 0.01, and 0.9 squared would be 0.81, so it's going to be 0.18. Okay, Now, note that there are 80 students in the first group, so 80, 40, 20. So we have to take the averages, weighted averages of 80, 40, 20, okay? So the total G is the weighted average, which is 80 times 0.5 plus 40 times 0.42 plus 20 times 0.18, and then you divide it by 80 plus 40 plus 20, which is 140. So let's see what that gives us. Okay. So we have 40, because 0.5 times, because 0.5 times 80 is 40, so let's just put 40. Then plus, we have 40 times 40, 0.42. I'll just write that down. 40 times 0.42 plus 20 times 0.18. And then you divide the entire thing by 140, because 80 plus 40 plus 20 is 140. And if we calculate it, it's 0.43142. 43142. Okay, so this is C. If the Gini impurity index becomes 0, which of the following is false? Okay, well, we just saw that when Gini impurity index is 0, then because in this formula, if you have 1 or 0, that means probability of these. So when you have only one possibility, which means you only have one probability, which is 1, the Gini impurity index will give you 0. So it's called Gini impurity index because if you have only one possibility, everything is of the same possibility, then it's perfectly pure. That has Gini impurity index 0. But in the previous case, we also saw that if you have only one possibility, entropy is also 0. So in those cases, they both agree. Entropy and Gini impurity index both become 0 if you have a probability which is 1, which means that everything is the same thing in that group. There is no more decision to be made because in a decision tree, you try to make a decision, and if your set only has one outcome, then that becomes the leaf node. You say, if everything is accepted as cadet, then the decision will be this person is accepted for cadetship, something like that, right? And then it means that the set now contains only one of the classes. Okay, so it's the same thing. So A, B, C are all correct, so D must be wrong. Yeah. Now, which of the following algorithm uses the Gini index to determine the decision criteria? Well, I actually don't know about conditional inference trees. This seems to be using something completely different, but what you do have to know is that ID3 algorithm and C4.5 are algorithms that uses the entropy to figure out the best feature to make decisions. And CART is the one that uses the Gini impurity index. Okay, although you can take the CART algorithm and switch out the Gini to the entropy. The default for CART is Gini. Okay, so the answer for this would be CART. Okay, which of the following is an ensemble learning algorithm? So the last two questions are about the random forest. And random forest makes a bunch of different decision trees to come up with a aggregated conclusion. If most of the trees say, oh, this person should be in group A, then that's the conclusion. And the way that we grow trees in the random forest is by using bootstrapping, which means you don't use the entire data, but you sample from the data. So you only use a partial of the data, and also we only use some partial of the features. We don't use all the features. We would just select some features. So different trees in the forest will have different conclusions, and then you just have those trees vote to see what should be the outcome. Okay, so such a learning algorithm is called ensemble learning algorithm, and the reason that we want to do ensemble learning algorithm is because it reduces overfitting. So decision trees are known to be highly sensitive to outliers, and therefore, if you just use decision trees, often you might end up with decision trees that may look okay, but give horrible outcomes for certain data points just because of your training set. Okay, so and that's what's written here. So bagging is bootstrapping, aggregating. So bootstrapping, so B, and aggregating AGGs. That's why it's called bagging. And bagging is what random forests do. It builds different trees by bootstrapping, and then it aggregates the conclusions to give a conclusion. So that's what random forests do. And the purpose for doing it is it reduces overfitting. So that's good. Okay. It creates machine learning models from bootstrap data and combines the data. Yes, so that's good. It makes more accurate predictions than single trees, especially when you have say individual trees are highly susceptible to outliers. So C is also true. Now it's false to say that it's quicker to train than a single decision tree because a single decision tree is just one single tree, so it's going to make a decision quickly. But for random forest, you need to ask many different trees for the conclusion, and you have to vote. So it takes more time to come up with a conclusion than a single decision tree.